Neptune drifts far beyond the bright planets we see in the night sky. It is a cold, blue world that hides a stormy heart. Its size is larger than Earth's but far smaller than Jupiter's. The planet's thick veil of gas hides pressures that crush anything we can imagine. We are only beginning to sense what lies beneath. I start with the numbers that give the planet its bulk. Neptune carries about 17 times the mass of Earth, yet its radius is only 3.9 times larger. Compared with Jupiter, which is roughly 318 Earth masses and 11 Earth radii, Neptune feels like a middle child, heavy enough to bend light, small enough to fit inside a gas giant's envelope. The mass-to-radius ratio tells us the interior must be squeezed tightly, a fact that will echo through every layer we examine. The distance from the Sun adds another piece to the puzzle. Orbiting at roughly 30 astronomical units, Neptune receives only a fraction of the sunlight that warms our own world. The solar energy that does arrive is spread thin, leaving the upper atmosphere at a chilly 55 Kelvin. I can almost feel the cold on a telescope dome, a thin breath of air that would freeze water instantly. That low temperature at the top is only the first step down a steep gradient. Below the pale clouds, the atmosphere changes composition and pressure in a way that feels almost industrial. Hydrogen and helium dominate, just as they do on the larger gas giants, but a noticeable fraction of methane gives Neptune its characteristic azure tint. Methane absorbs red light, leaving the reflected glow blue. The gas mixture is light at the top, but each meter deeper adds a few hundred bars of pressure. I find it hard to picture a column of air that thick, yet the measurements are clear. The pressure climbs faster than temperature at first. From the cloud tops down to a few thousand kilometers, the pressure rises from a few bars to a million bars, while the temperature climbs from 55 Kelvin to several thousand Kelvin. The increase is not linear. It accelerates as the material becomes more compact. Imagine a hand squeezing a balloon until the rubber feels like steel. That is the feeling of a fluid that has been forced into a denser state by the planet's gravity. The deep mantle is where the story becomes truly extreme. At depths where pressure reaches several million atmospheres, hydrogen ceases to behave like a gas and adopts metallic properties. Electrons flow freely, and the material conducts electricity like a metal. The temperature there is high enough to melt rock on Earth, yet the pressure keeps everything in a fluid state. I don't really know how a liquid metal feels, but the physics suggests it is dense, heavy, and unyielding. Why does Neptune serve as a natural laboratory for high-pressure chemistry? The combination of abundant carbon in methane, crushing pressure, and scorching heat creates conditions rarely found elsewhere in the solar system. In a laboratory on Earth, we must build diamond anvil cells to reach a few hundred gigapascals. Neptune does that on a planetary scale without any machinery. The planet's interior is a testbed where carbon can rearrange into forms that would not survive at the surface. The scale of the interior is staggering. Imagine a column of water a kilometer deep. Its pressure at the bottom is about 100 atmospheres. Now multiply that depth by 1,000, and you are approaching the pressures found a few hundred kilometers beneath Neptune's clouds. The numbers climb to millions of atmospheres, a pressure that would crush a submarine hull in an instant. The temperature, meanwhile, climbs to 3,000 or 4,000 Kelvin, hot enough to glow red, but hidden beneath layers of gas that keep the heat from escaping. The gradient also influences the planet's weather. Strong winds whip the upper clouds at speeds exceeding 2,000 kilometers per hour. Those winds are driven by heat escaping from the interior, a slow leak of thermal energy that powers storms larger than Earth itself. The same pressure that forces carbon into compact forms also drives the circulation that shapes the visible bands. I sometimes wonder whether the storms are merely surface expressions of the deep, unseen forces. Even the magnetic field hints at the interior's oddness. Neptune's magnetosphere is tilted and offset from its rotation axis, suggesting that the dynamo region, where moving conductive fluid generates magnetic fields, lies in a shell rather than a central core. The shell is likely composed of that metallic hydrogen-helium mixture we mentioned earlier, swirling under the weight of the overlying layers. The field is weaker than Jupiter's but still strong enough to trap charged particles. All these pieces fit together like a puzzle whose picture we have never seen in full. The mass and radius tell us the planet is dense enough to compress its gases. The composition tells us carbon is present in large amounts. The pressure-temperature profile shows us a path from icy clouds down to a hot, metallic sea. Together, they set the stage for chemical reactions that would be impossible elsewhere. There are still gaps in the data. We have only a handful of spacecraft flybys, and most of the interior must be inferred from models. I don't really know how accurate those models are when they extrapolate beyond laboratory conditions. We don't really know the exact state of matter at 10 million atmospheres, or how the mixture of hydrogen, helium, and carbon behaves under those extremes. The uncertainty is part of the intrigue. What remains clear is that Neptune is not a simple ball of ice and gas. It is a layered world where pressure climbs by orders of magnitude, where temperature rises from a frigid veil to a scorching interior, and where chemistry is forced into regimes we can only simulate on Earth. The planet's bulk properties, mass, radius, distance from the Sun, are the anchors that let us build a picture of those hidden depths. As I write these notes, I can hear the faint hiss of a spectrometer measuring methane lines in a distant spectrum. The data whisper of a world where carbon atoms are squeezed together, perhaps forming structures that would glitter if we could see them. I find it hard to picture a rain of such structures falling through clouds, yet the pressure profile suggests that somewhere deep below, the conditions are right for them to form. A final observation. The pressure at a depth of about 2,000 kilometers reaches roughly 1 million bars, a point where hydrogen transitions from a molecular to a metallic state. That boundary, thin as a sheet of paper in planetary terms, marks the start of the region that could host exotic carbon chemistry. It sits just below the region where the visible clouds end. Methane dominates the upper layers of Neptune, its pale violet hue a reminder of countless carbon atoms drifting in a cold wind. Each molecule carries 4 hydrogen atoms bound to a single carbon, a tiny reservoir waiting for pressure to rewrite its chemistry. In the planet's lower atmosphere, that reservoir becomes a laboratory without walls. Pressure on Neptune climbs quickly once we descend a few hundred kilometers. It reaches millions of times Earth's sea level value within 1,000 kilometers. At such forces, carbon-hydrogen bonds cannot hold. The hydrogen is stripped away, leaving carbon atoms pressed together. The process is not a sudden snap but a gradual polymerization, where small hydrocarbon fragments link into longer chains. Laboratory work on Earth mimics this by squeezing methane-rich samples inside diamond anvil cells. Researchers raise pressure to the gigapascal range, 1 billion pascals, while heating the sample to a few thousand Kelvin. Under those conditions, the methane first breaks apart, then reorganizes into more complex hydrocarbons, and finally collapses into a dense carbon lattice. The resulting solid is not graphite. It is a 3-dimensional network that we recognize as diamond. The experiments show a clear pressure threshold. Above roughly 20 GPa, carbon prefers the tetrahedral arrangement of diamond rather than the planar sheets of graphite. Temperature plays a subtle role. Hotter conditions shift the balance, allowing the lattice to stay stable even as pressure fluctuates. In the lab, we can watch the transition on a microscope screen, a faint glow indicating the birth of a new crystal. On Earth, diamond formation occurs deep in the mantle, where pressures of 5-6 GPa and temperatures around 1200 degrees C allow carbon to crystallize slowly over millions of years. Those diamonds are later brought to the surface by volcanic eruptions. Neptune's interior pushes the pressure far beyond that mantle range, up to hundreds of gigapascals, while temperatures climb to several thousand Kelvin. The same carbon atoms therefore experience a much harsher environment, and the resulting diamonds are expected to be larger and form more rapidly. The key difference lies in the surrounding gases. In Earth's mantle, carbon is mixed with silicates. On Neptune, it is dissolved in a sea of hydrogen, helium, and methane. This hydrogen-rich matrix changes the way carbon atoms meet each other. Instead of a slow, diffusion-limited encounter, the high density forces collisions at a rate that can outpace the removal of hydrogen. The hydrogen is expelled as a gas, leaving behind a carbon skeleton that quickly snaps into a diamond lattice. Laboratory simulations also reveal that once a diamond seed appears, additional carbon can accrete onto its surface, growing the crystal like a snowflake in reverse. The growth front moves outward, adding layers of carbon atoms as long as pressure and temperature remain within the stability field. In the lab, we see crystals reach micrometer sizes before the sample is quenched. On Neptune, there is no quench, only a continuous supply of carbon from the surrounding methane. Temperature, however, does not simply melt diamonds. At the extreme temperatures found near Neptune's 3,000 kilometer depth, diamond remains solid because pressure dominates the phase diagram. If pressure were to drop sharply, the same temperature would melt the crystal into a liquid carbon phase. The balance is delicate. A modest rise in temperature can shift the stability window, favoring a semi-fluid carbon that behaves more like soot than a gemstone. We have measured the electrical conductivity of these high-pressure carbon phases. Diamond, an excellent insulator at Earth's surface, becomes surprisingly conductive under megabar pressures. This conductivity hints that the interior of Neptune may host a layer of semi-metallic carbon, a conduit for heat and possibly magnetic effects. The lab data are still noisy, and we don't really know how large such a conductive layer might be. The methane supply itself is not infinite. Spectroscopic observations show that the upper atmosphere contains abundant CH4, but deeper layers are depleted as carbon is locked into solids. Models suggest a steady downward flux of methane, replenished by vertical mixing. That mixing is driven by convection, the same process that stirs Earth's oceans. In Neptune, the convection cells are massive, transporting methane parcels over thousands of kilometers in a matter of hours. When a parcel of methane-rich gas sinks, it experiences a pressure increase of roughly 10 MPa per kilometer. Within a few hundred kilometers, the pressure is already high enough to force carbon atoms together. The hydrogen released during polymerization rises back toward the surface, forming a faint, invisible plume of H2 that we cannot yet detect directly. The carbon, however, stays behind, joining the growing crystal. Our models predict that the resulting diamonds can range from microscopic grains to macroscopic raindrops, perhaps a few centimeters across. The size distribution depends on the rate of methane delivery, the local pressure gradient, and the temperature profile. In the lab, when we limit the methane supply, only tiny grains form. When we flood the chamber, larger crystals appear. Extrapolating to Neptune, a region with a steady, abundant methane flux could produce a rain of sizable diamonds. The concept of diamond rain is tempting, but the reality is more subdued. The diamonds are not glittering gems falling through a clear sky. They descend through a thick, turbulent sea of hydrogen, helium, and silicate vapor. Their descent is slowed by drag, and they may melt temporarily if they encounter a local pressure dip. Some may reach the deep interior, adding to a core of solid carbon that could be many kilometers thick. We have not yet measured the exact depth at which diamonds begin to form. Laboratory data give us a pressure-temperature curve, but the planet's interior is not perfectly uniform. Small variations in composition, temperature, or magnetic field could shift the formation zone by hundreds of kilometers. I find it hard to picture a single, sharp boundary where methane instantly becomes diamond. Even if diamonds form, their fate after creation is uncertain. Some may be lofted back upward by powerful updrafts, re-entering regions where pressure drops below the stability threshold. In those zones, the diamonds could revert to a carbon fluid, dissolving back into the surrounding gas. This cyclical process could recycle carbon many times before it finally settles. The laboratory work also shows that other carbon allotropes, such as lanstellate, a hexagonal form of diamond, can appear under shock conditions. Neptune's interior may experience occasional shock waves from impacts or internal convection, providing brief spikes in pressure that favor these exotic structures. We have not yet reproduced those exact conditions, so the presence of lanstellate remains speculative. One practical consequence of carbon solidification is its effect on Neptune's heat transport. Solid diamonds have higher thermal conductivity than the surrounding fluid, potentially channeling heat from the deep interior toward the outer layers. This could influence the planet's observed excess heat emission, a long-standing puzzle for planetary scientists. Our current models lack precise values for diamond conductivity at megabar pressures, so the impact remains an open question. We can compare this carbon behavior with that on Earth, where diamond formation is a rare, localized event. On Earth, the presence of water and other volatiles can lower the pressure needed for diamond growth, but the overall carbon budget is small. Neptune, by contrast, has a carbon reservoir measured in billions of tons, and the pressure is always high enough to keep diamonds stable. The contrast highlights how planetary context reshapes a simple element's destiny. Temperature also determines which carbon phase dominates. At lower temperatures, graphite is the preferred form, arranging carbon atoms in flat sheets. At the higher temperatures of Neptune's deep atmosphere, those sheets cannot persist. The thermal energy pushes atoms out of the planar arrangement, encouraging the three-dimensional tetrahedral network. In the lab, we see this transition clearly when we heat a graphite sample under pressure. It converts to diamond without any catalyst. The hydrogen liberated during polymerization does not simply escape. It can recombine with carbon to form acetylene or other hydrocarbons, which then re-enter the pressure-induced cycle. This secondary chemistry adds complexity to the carbon budget, creating a web of reactions that our simplified picture does not fully capture. We don't really know how much of the original methane ends up as diamond versus remaining in gaseous form. Observations from spacecraft have detected spectral signatures that hint at the presence of solid carbon particles high in the atmosphere, but the data are ambiguous. The signatures could arise from soot like carbon, not necessarily diamond. Future missions equipped with high-resolution spectrometers might separate those signals, giving us a clearer picture of where diamonds truly form. In the end, the path from methane to diamond on Neptune is a chain of pressure-driven steps, each governed by well-understood physics yet complicated by the planet's scale. Laboratory experiments give us a roadmap, but the map is incomplete, with gaps where temperature, pressure, and composition intersect in ways we cannot fully replicate. A small, steady hiss of hydrogen bubbles can be heard at the 500-kilometer level, marking the depth where carbon finally chooses the diamond lattice. The pressure at the mid-level of Neptune's envelope reaches a few million bars, a regime where ordinary gases give way to exotic liquids. In that environment, carbon, carried aloft as methane, begins to feel the squeeze of 1,000 kilometers of overlying mass. Laboratory experiments on carbon-rich fluids suggest that once the pressure exceeds roughly 1 gigapascal, the atoms arrange themselves into a lattice that can serve as a seed for a diamond. At depths between 1 and 2,000 kilometers beneath the visible cloud deck, the temperature still hovers near 2,000 Kelvin. Under those combined conditions, the free energy of a carbon atom in a liquid becomes lower when it joins a crystal than when it remains dissolved. Theoretical calculations place the onset of favorable nucleation precisely in that band. I find it hard to picture a single atom deciding to lock into a solid, but the statistical picture is clear. Enough atoms line up, a tiny seed appears, and the surrounding carbon begins to accrete. Growth proceeds by adding layers of carbon onto the seed, much like frost building on a cold pane. The rate depends on how much methane is still being broken apart by the intense heat. Models show that a seed a few nanometers across can double its radius in a few hours, eventually reaching sizes of several micrometers. At that point, the crystal is no longer a speck of dust, but a solid particle with a density near 3.5 grams per cubic centimeter, much heavier than the surrounding hydrogen-helium mixture. Gravity does not let the particle linger. Using Stokes' law adjusted for the high-pressure fluid, researchers estimate a terminal velocity of a few centimeters per second for a micrometer-scale diamond. That sounds slow, but over the distance of 1,000 kilometers, the descent takes weeks, not years. The slow drift allows the crystal to encounter layers of varying temperature and composition, which can either add to its mass or erode it if the surrounding chemistry changes. Convective currents in Neptune's deep atmosphere move at speeds of several meters per second, far faster than the settling rate of a single diamond grain. When a rising plume carries methane upward, it also drags existing diamonds upward for a time. As the plume cools, the diamonds detach and resume their slow fall. The interaction creates a complex pattern. Some particles linger in a quasi-steady layer, others plunge in narrow, down-welling streams. The term diamond storm has been tossed around, but the reality is a patchwork of localized downflows rather than a planet-wide deluge. Heat transport in the mantle is partly mediated by these solid particles. As diamonds sink, they carry thermal energy from hotter depths toward cooler layers, supplementing the usual convective motion of the gas. Calculations suggest that the contribution is modest, perhaps a few % of the total heat flux, but it is not negligible. The presence of solid carriers changes the effective viscosity of the fluid, a factor that feeds back into the overall circulation pattern. The size distribution of the diamonds is not uniform. Smaller seeds are constantly generated at the nucleation depth, while larger crystals are the survivors of many weeks of descent. Simulations predict a tail of particles reaching centimeter scale before they melt or dissolve as they approach the upper atmosphere. Those larger gems would fall faster, perhaps reaching a few decimeters per second, yet still far slower than the surrounding wind. One point that remains uncertain is the exact composition of the surrounding liquid. If sulfur-bearing compounds are abundant, they could alter the carbon chemistry, either promoting or suppressing crystal growth. Laboratory work at comparable pressures shows that small amounts of nitrogen can poison the lattice, slowing the accretion rate. We don't really know how much of those impurities Neptune carries, so the models carry a margin of error. Another subtlety lies in the way the diamonds affect the planet's magnetic field. Conductivity of the deep fluid is already high, but the inclusion of solid carbon could introduce anisotropies. The effect is likely tiny, yet it illustrates how a seemingly isolated process can ripple through the planetary system. Observations from the Voyager 2 flyby hinted at unexpected opacity in the infrared, a clue that solid particles might be present. Subsequent telescopic spectra have not resolved individual diamonds, but they do show a muted signature where methane absorption should dominate. Whether that dimming is due to rain like diamonds or to other condensates is still debated. In the end, the picture that emerges is one of a slow, steady rain of carbon crystals, born at a precise depth, growing in a hostile liquid and drifting downward under a gentle pull. The process is neither dramatic nor instantaneous. It is a quiet conversion of gas into solid that proceeds over months, hidden beneath layers of clouds. A single micrometer diamond, after weeks of falling, will finally reach a region where the pressure drops below the stability threshold and it vaporizes, returning carbon to the gas phase. That final act completes a loop that may repeat endlessly, a subtle cycle that keeps the deep atmosphere of Neptune in a state of quiet exchange. The notion of diamonds raining down on Neptune feels like a story told in a dimly lit lab, half remembered and half measured. We have never caught a crystal falling from that distant sky, yet the clues gathered over decades keep the idea alive. Spectra taken from Earth-bound telescopes show faint bands where methane and other hydrocarbons absorb sunlight. Those same bands sometimes carry a subtle extra dip, a whisper of soot like particles suspended high above the cloud tops. When I stare at those graphs, I find it hard to picture how a thin haze of carbon could hide solid gems beneath. Voyager 2, the lone spacecraft that ever brushed past Neptune, sent back a thin stream of data on temperature and composition. Its instruments recorded a sudden rise in pressure at depths where the temperature still hovered near a few thousand Kelvin. The numbers line up with the pressures needed to squeeze carbon atoms together, but the probe never carried a camera that could photograph a falling stone. Back on Earth, researchers have tried to mimic those conditions in the lab. Using a powerful laser, they drive a shock wave through a tiny sample of methane-rich gas. The wave compresses the gas to pressures exceeding 1 million atmospheres, temperatures rising to several thousand Kelvin. In the aftermath, tiny soot-like spheres appear, some of them glittering like miniature diamonds under a microscope. The experiments are elegant, but they also remind me that we are watching a flash, not a steady rain. Uranus offers a quiet comparison. Its atmosphere, composed of similar gases, shows the same spectral quirks, those faint soot signatures that hint at carbon condensation. Yet the planet's lower internal heat makes the pressure profile different, and no one has claimed diamonds there either. The parallel is useful, but it also shows how easily we can over-interpret a pattern. One might argue that the spectral dips are simply unburned hydrocarbons, not solid carbon. The data can be fitted with models that keep the particles in a gaseous or liquid state, avoiding any need for a crystal lattice. Those models work, but they require assumptions about mixing and cloud dynamics that we cannot verify from a distance. The Voyager measurements of temperature gradients add another layer of doubt. The probe sensed a sharp temperature drop just before the pressure climbed, a region that could host a supercooled liquid rather than a solid. If the carbon condenses as a liquid, it would not form the lattice we associate with diamonds, and it would behave more like a tar-like drizzle. Laboratory shock experiments, however, reveal a different outcome when the compression lasts longer. Extending the laser pulse by a fraction of a microsecond allows the carbon to crystallize, producing nanometer-scale diamonds that survive the rapid cooling. The timing is delicate. A slight change yields amorphous carbon instead. This sensitivity tells me we are still guessing where Neptune sits on that narrow timeline. Uncertainties pile up when we consider the planet's weather. Neptune's winds roar at over 1,000 kilometers per hour, whipping any falling particle into a chaotic tumble. A diamond that forms deep within the atmosphere would have to survive a long, turbulent descent, possibly melting or breaking apart along the way. We have no direct evidence of such survival, only the theoretical possibility. Alternative explanations linger in the data. Some researchers suggest that the soot-like particles are simply complex organics, the result of photochemical reactions driven by ultraviolet sunlight. Those organics could aggregate into fluffy aggregates that mimic the scattering signature of small diamonds. The hypothesis fits the observations without invoking high-pressure crystallization. Even the high-pressure experiments leave room for doubt. The samples are tiny, no larger than a grain of sand, and the conditions are achieved for only microseconds. Scaling those results to a planetary atmosphere, where pressures persist for hours or days, is a leap. We don't really know whether the same pathways dominate under Neptune's steady conditions. The most persuasive piece of indirect evidence remains the coincidence of pressure, temperature, and carbon abundance predicted by models. Those models, built on equations of state derived from lab work, suggest a diamond zone a few thousand kilometers below the visible clouds. The zone sits where methane breaks down, releasing free carbon that can be forced into a lattice. The math is tidy, but the planet refuses to hand over a single photograph. Voyager's magnetometer detected a subtle anomaly in the magnetic field, a blip some have linked to conductive material moving within the planet. Conductive diamonds are a stretch, yet the idea illustrates how we sometimes stretch data to fit an appealing narrative. The anomaly could be caused by many other things: metallic hydrogen, ionized winds, so the link remains speculative. When I compare the lab results to the remote observations, the picture feels like a puzzle assembled from mismatched pieces. Each piece, spectral dip, pressure reading, shock-induced crystal, offers a hint, but none completes the image. The gaps are as instructive as the clues themselves, reminding me that the universe often resists tidy explanations. One small, concrete detail stands out. The laser-driven shock experiments consistently produce a faint greenish glow in the aftermath, a glow that matches a weak emission line seen in Neptune's upper atmosphere. That coincidence lingers in the data, a quiet reminder that somewhere, deep within the blue-green swirl, carbon is being forced into an unfamiliar state. The idea that solid carbon might drift down through a planet's clouds feels like a laboratory note written in a notebook that has been left in a cold drawer for years. It forces us to ask whether the heat that Neptune radiates into space is carried, in part, by tiny shards of diamond slipping through layers of gas. If those crystals form near the 1,000 kilobar mark and then sink, they could act like tiny heat pipes, moving energy from the deep interior toward the upper atmosphere. The effect would be subtle, but over millions of years it could change the temperature gradient that models currently assume. I find it hard to picture a rain of gemstones in a sky of hydrogen, helium, and methane. Yet laboratory experiments on Earth show that carbon dissolved in liquid hydrocarbons will crystallize when pressure reaches a few 100,000 atmospheres. The same chemistry, under Neptune's crushing weight, should produce a steady drizzle of microscopic diamonds. When those particles reach regions where the pressure drops, they may melt back into liquid carbon or remain solid, depending on the exact temperature profile. That uncertainty makes it difficult to predict how much heat they actually transport. If the diamonds survive their descent, they will eventually reach a region where pressure climbs beyond the diamond stability field, and carbon may adopt more exotic arrangements. Theoretical work suggests that at pressures above a few terapascals, carbon could rearrange into a super-dense phase called carbide-like, or even a metallic form. Those phases would conduct heat far more efficiently than the surrounding fluid. In that sense, diamond rain could be a prelude to a deeper carbon ocean, a hidden layer that we have yet to confirm. The picture reminds me of the way helium behaves in Saturn's atmosphere. Helium droplets form and fall, releasing gravitational energy that contributes to Saturn's excess heat. Jupiter, on the other hand, hosts metallic hydrogen that conducts electricity and generates a magnetic field. Neptune's diamond rain sits somewhere between those two phenomena. It is not a direct analog, but the comparison highlights how phase changes in an atmosphere can shape a planet's thermal budget. Each ice giant may have its own version of a rain that we have only begun to catalog. We do not really know how large the effect is. Existing models treat the interior as a smooth fluid, inserting an average opacity and a simple equation of state. Adding a population of solid particles forces us to rethink that simplicity. The particles could scatter infrared radiation, altering the planet's observed spectrum. They could also provide nucleation sites for other condensates, subtly shifting cloud layers that spacecraft have never sampled directly. Future missions could test these ideas, but the engineering challenges are formidable. A probe that survives the plunge through several thousand kilometers of atmosphere would need a heat shield capable of withstanding temperatures above 2000 K and pressures that crush most metals. Some concepts propose a soft landing capsule that deploys a series of parachutes made from high-temperature composites, then drifts for weeks while recording pressure, temperature, and particle density. Others suggest a remote sensing approach, a space-based telescope equipped with a spectrograph tuned to detect the faint absorption features of solid carbon at specific wavelengths. The signal would be weak, but with long integration times, a pattern might emerge. Even a modest orbiting spectrometer could look for the telltale signature of Diamond's Raman shift, shifted by the planet's gravity. If that line appears at the expected depth, it would be a strong hint that solid carbon is present in the upper layers. A more ambitious concept involves a swarm of tiny, disposable probes released from a carrier spacecraft, each designed to transmit a brief burst of data before being crushed. The swarm would map the vertical distribution of particles, giving us a three-dimensional picture of where the rain begins and ends. Beyond Neptune, the idea of carbon precipitation may help us interpret the spectra of distant exoplanets that orbit far from their stars. Some of those worlds are classified as cold giants with thick envelopes of methane and water. If their interiors reach similar pressures, they too might host diamond formation. Detecting such processes could inform estimates of a planet's bulk composition, its thermal evolution, and even its potential to retain a magnetic field. The ripple effect spreads through planetary science, connecting a single hypothesis to a broader framework for interpreting alien worlds. Human fascination with gems adds an unexpected cultural layer to the scientific discussion. The notion that a planet could literally rain diamonds captures the imagination, yet the scientific value lies in the physics of phase transitions under extreme conditions. By focusing on the mechanics rather than the sparkle, we keep the inquiry grounded. Still, the image of a distant sky littered with tiny, glittering particles offers a reminder that even the most abstract calculations can evoke vivid mental pictures. One detail that keeps resurfacing in laboratory notes is the measured latency between pressure increase and crystal nucleation. In a high-pressure cell, carbon takes on the order of seconds to form a detectable diamond lattice once the threshold is crossed. If a similar delay exists in Neptune's atmosphere, then a parcel of gas could travel several kilometers before the first crystal appears. That distance sets a scale for the thickness of the rain zone, a thin shell where solid carbon coexists with liquid. It is a small piece of data, but it anchors the larger picture in something we can actually measure.